Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay back with yet another geometry video for you all. And today's topic discussion is on one of my very own favorite topics, something that's not often covered in geometry topics and geometry courses. And that's what we're all about here at eCoreAcademy, striving to go towards those enrichment topics. So this is all about conic sections and rotated figures. Now, this is a large topic, but I've broken it up into sections that are bite-sized sections, and I will be going through them as efficiently as possible, making the most of your time to really get out of this course. But before we jump into today's topic, please make sure to smash that subscribe button down below, hit that like button on this video, and turn on post notifications right next to that subscribe button, that little bell icon, to make sure you're up to date on every single one of our latest posts on our YouTube channel. Also, feel free to utilize the comment section down below to leave down any of your new suggestions for videos, any of your feedbacks that we will try and implement in our videos to come. It will not go unnoticed. So what are the specifics that we're going to be looking at? We're going to take a look at conic sections and rotated figures as well. So conic sections are types of rotated figures, and then we'll take a whole entire different lesson to actually discuss rotated figures and 3D intersections of figures. But today we're mainly focused on conic sections and how they're developed from a rotated generic line, or a generating line, also known as your general axis. And I'll show you exactly what that situation comes about. All of this revolves around something called the double napped cone, and I will discuss that in depth originally, and then we'll go into the different types of conic sections that there are available. And I'm sure many of them, if not all of them, you're already familiar with, but it's a very new type of setup that we're trying to distinguish these sections from each other and try and discover how they're going to be created or expressed as rotated figures, as I've shown you here in our little agenda for our lesson for today. But without further ado, let's jump right into it. So let's take an introduction into conic sections. Where did they come about, and what exactly do they revolve around? So what are conic sections in short? Conic sections are two-dimensional figures developed by the intersection of a double napped cone generated by a diagonal line. Now, that might seem like a mouthful and a lot to memorize, but it's not really there to memorize. You guys should not attach a definition to this topic. I'm giving you this here just to show an enrichment, a higher correlated topic with this, but when you're trying to think of conic sections, think of a figure, which I'll show you below. So the GIF below, these two GIFs below, these were supposed to be GIFs. They did not turn out as GIFs. I apologize, but I will show you a GIF in my next video. I'll try and implement that. I had to do something different with our template, but I will adjust that. So I'll show you the GIF of exactly how it creates this cone. But these pictures below show a line that's being rotated along an axial direction to develop two congruent cones that are placed on top of each other. So in short, a conic section is created when you have a diagonal line, and I will draw that diagonal line out. So if we have a diagonal line like this, not horizontal or perpendicular, horizontal or vertical, it's going on a slant in any way that's greater than 0 degrees. And as you can see here, this diagonal line, what's basically happening is this diagonal line is being rotated across like this. It's being rotated along its center, keeping the same diagonal property, and it's being rotated along a 3D axis. And when it's doing that, it's just going to do this. It's going to create this portion here, like this part of your cone, and then it's going to create that bottom half of your cone. Oops, forgot to create that circular base. It's going to create that circular base here as well to create that double napped cone, as you see here. So this line right here, I'll just trace it out. This is a line basically being rotated across this way. And as you can see here, it's being rotated along this entire line to create these two cones going in opposite directions, as shown for the bottom and top. And when those lines are rotated, they create cones. Because what happens is, if you're taking a look at a line right here, let me redraw that line. When you're rotating amongst the top, what you're going to do is you're going to create a circle, basically. That circle is the base of your cone. But as you start to go towards the center of the line, it becomes skinnier and skinnier as it leads up to a singular point. And that's exactly how you create your cone here. Now, why does it create two cones? Well, if you look here at this diagonal line, and we split it in half right here, this top half is going to be moving counterclockwise, so counter. And this bottom half of this line, this bottom half of this diagonal line is going to be moving in a clockwise. Whoa. Auto-corrected my text. All right, clockwise. Yeah, we have autocorrect text. That's cool. So we have counter. Oh my, that apologize for that. So counter and clockwise. So this is going in the opposite direction, counter against the clock in which it moves. And then the clockwise is moving in the direction of a clock. So it's going to be forming that same circle, but moving in opposite directions. That's why you're going to have two different cones develop. If you only had one half of this entire line and it would be array, if it were array, then it would only create one cone. But since it's a line, it creates two cones that directly connect each other at one common point called the vertex, which I'll get into in the next slide. And they develop two congruent cones. So these two cones are also going to be congruent. Write that right here, congruent cones. And yes, as I was saying, a line is basically twice as much as an array in terms of infinite solutions. Therefore, you're going to have two different cones created. And of course, because they're lines, we don't exactly know the exact amount, the area of these cones, of these conic sections, but all we do know is that these lines are going to somehow form those cones, and that's all that we need to know in order to develop our intersections. And all we need to know is that the cones actually intersect each other at that vertex. They meet at that common vertex. They're going to be congruent, and they're twice as much as that ray created. They're going to be that line creation of those cones, so that's why it's double the amount. And we know that these conic sections are going to be properties of intersections of these double-napped cones. So let's get right into it. The first type of demonstration with our cones, and that's going to be determining the different parts of our double-napped cone. So parts of the figure is what we're going to be focusing on. What are some of the basic parts of our double-napped cone, and how can we actually dissect it in order to move on and figure out what these different conic sections actually are? So the first and most important part of this entire cone is going to be your central axis, and it's the center of both the cones in which the generator spins upon. So we have that horizontal line, which is called our generator line or our generating line. And what happens is that line has to have some sort of axis to bend upon or turn upon, because that line can actually start to turn steeper, or it can start to change at a steeper motion or a much shallower motion, in which it's much longer than it is wider. So that central axis is in which the point in which the entire generating line spins upon, that entire line that it spins upon, that central line of your cones. And then you have a generating line, which is the line itself that creates the cone while it's spinning along that axis, that diagonal line that spins across. And then, of course, you have your vertex, which is the central point of the central axis, and it's the contact between both cones. So it's the central point in which both cones connect. So what is the central axis on this point? So we have the central axis. It's going to lead directly through the center of these cones. And then this is going to be our that generating line, our diagonal generating line right here. And it's going to spin across this line with the center at here, this central axis, around this central axis. And then what we also have here is our vertex. So this is going to be our vertex. This is going to be the contact point between both of the double napped cones, and it's also going to be the very center of this entire figure itself. All right, so let's move on. Now that we know the basic parts of this entire double napped cone, we can start to identify different intersections of the cone and different properties of it as well. So let's start off with our first conic section. This is our parabola, something that you should be familiar with, and we will get into as well. We will get into this as well throughout the course of conic sections, and we'll get through parabolas and all of its specific types. But I want to show you how it's technically created in geometry and where are its origins from. So these are called parabolic intersections. So a parabola, in terms of a double napped cone, I know it has many other definitions, especially in Algebra 1 and Algebra 2. But when it comes to geometry in total, we refer to it in conic section form because it is a figure in geometry. So a parabola is when a plane intersects the top or the bottom cone of a double napped cone with a line that has a diagonal degree of direction and intersects the vertex. That's also a mouthful, but don't worry, I'm going to explain that. If we take a look at our given conic section here with our double napped cones, as you can see here, a parabola kind of looks like this. I'm sure many of you should already be familiar with this in geometry, in Algebra 1. This is basically a quadratic form of a parabola. A parabola is basically a U-shape that extends infinitely above in those two directions. So what's happening here is you're going to have a plane, that intersects one of the two cones. So in this case, it only intersects one of the two cones. In this case, it's only intersecting the top. It will never touch the bottom cone. It only intersects one cone. And what it basically does is it's going to be a certain type of figure in which a plane, we know that a plane is basically it refers to a three-dimensional outlook. That plane is a three-dimensional outlook that only has a set distance, an infinite distance, 2D outlook on a 3D outlook, on a 3D overview. So that's our plane right there. And it's when that plane kind of slides into that top cone and intersects it at 2 points. So it's going to intersect it at 1 point and 2 points that is parallel to either of the generating lines. So it's going to be parallel to this line right here. And when it's parallel to this line, or if it only intersects the base or one other side, it's going to create that parabola as we see here, that U shape. And it can be slid across or beyond until it reaches this generating line. Or it can also intersect the vertex itself. So it can intersect the vertex here and create that same exact U shape. So that's an example of how we create our parabolas. And some properties of parabolas that you should know is that parabolas have common equations, and they can be expressed in vertex and standard form, and they're quadratics. That's where our quadratic equation derives from. We know that our lines are going to be going on infinitely, but one thing that we do know is that we know our known vertex. We know this position on this line. We know where that is in distance from our vertex. However, we don't know these extended lines. That's where we get this whole parabola concept from, in which our lines extend out infinitely in this manner. And of course, we have our two forms, which are vertex and standard form, which we will get into in our specific lessons. But I'm sure you're familiar with vertex form, which is y equals a times x minus h squared plus k, in which x is always being squared. X will always be squared, and that's where this whole property of infinite comes from. Right here. This whole property of infinite doubles. So infinite doubles two lines that extend infinitely. Moving on to our next figure, we have our circles. So let's look at the intersection of a circle on a double napped cone, specifically one double napped cone, and I'll explain that in our definition. So a circle occurs when a plane intersects either the top or bottom cone of a double napped cone, and it's going to be perpendicular to the vertex. This is very important. We know that circles are very, very, very unique in the fact that they have equal degree measures, meaning they're going to be one consistent motion all the way around. If you were to use pen and paper, you would have to create that perfect circle, which is basically like a square in terms of, your polygons. They have to be perfect side lengths, so they're almost impossible to actually create. And circles can be expressed in two forms, which are standard and graphing forms. I'll explain that later. But let's first focus on the double napped cone and how it actually appears on the double napped cone. So if we take a look here, we know that it's a perpendicular plane. So that plane has to be perpendicular to the vertex of this cone, and it's only going to intersect one of the cones, the top or the bottom. So in this case, it only intersects the top. Just trying to emphasize on that, only intersects the top, and it never intersects the bottom, only one. Keep that in mind with the parabola and circle. You might want to write that down, or just really keep that in the back of your head. Memorize that, register that. These are two things. There's also another item that will also intersect only one. But we have the top and bottom. They're going to be separate intersections, so it's only going to intersect one of the two cones. So this plane is going to intersect the top cone in this case, but one of the cones in general. And it's going to be perpendicular to the base. So that means that the plane is going to intersect at a straight 90-degree angle right here. So if we take the central axis that we have, we draw that central axis here, it's going to form that 90-degree angle as we see here. 90-degree angle. So it's going to be directly perpendicular. Face is going to be facing directly towards the vertex in a straight manner, a straight line. And you're going to see how that forms an even circle all the way around. And the circle can be expressed in standard and graphing form. Just to give you a little insight on the standard form, you're basically going to be squaring both of your x and y values. So x is going to be squared, it's going to be to x squared, and y is going to be to y squared. Don't want to give it away just yet, and you might be confused as well, but I'm just trying to give you some insight. A circle, how it gets its perfect shape, you have to square both of your coordinates, both of your y-axes. So in order to square them, you're going to get that perfect shape all the way around your circle. On to our next shape. This is something that you're not necessarily going to cover in Algebra 1, but you're going to see in Algebra 2 and higher level math courses, but it's hyperbolas. But I just want to show you what it looks like in a figure form in geometry. Let's try and forget what we know in Algebra 1 and Algebra 2 in terms of these figures, and let's just focus on these ideals from basic scratch. So when you're looking at your parabolas and your hyperbolas and your circles, all you're focused on is calculating values, but we actually have to figure out where the origins of these figures come from. And that's the whole purpose of geometry. And that's why I'm so passionate about teaching this lesson right here. And this whole unit about conic sections is really to derive these figures and develop the relationships. So let's take a look at the intersection of a hyperbola. This might seem a little bit intimidating, but if you know what your parabola is, this should come instantaneously. So a hyperbola is when a plane intersects both double-napped cones. And of course, unlike our parabola and our circle, this is going to intersect both the top and the bottom cone simultaneously. And it is going to intersect through a diagonal plane or one that is directly parallel to the sides of the cones. So I'll show you what that means. If we take a look at this diagram here, what's happening is you're having a plane that's going to intersect so it can be directly parallel to your given central axis here. So let's draw our central axis like that. So this is our central axis. So with our central axis, it's going to be directly parallel to that axis. And when it does so, you're going to form two parabolas, like this one here and this one here. And on a graph, what would that look like? So we know that our two parabolas are formed, and we can see here that they're basically upside down versions of each other. So this is what a parabola looks like. Hyperbola looks like. It's basically a double parabola, as I state here in my next point. I say hyperbolas are reflections of two parabolas that both have opposite values for solutions through vertex and standard form, which are their equational forms, same as parabolas. And as we can see here, these are two parabolas which are reflections or direct opposite flip overs of each other. If you reflected them across a mirror, they would represent that opposite values, and therefore they have directly negative opposite values from each other. And all that's happening is here, this is an example of one situation in which it's parallel to your central axis and it's sliding across. You're always going to have 2 points, two little cups, two little parabolas formed that are going to be directly linked to each other, like this, just like this, like double opposite, upside down, used like that. But it can also be a diagonal. So you can also have it diagonally formed in which it's parallel to the generating lines as well. Those generating lines being these lines right here. Any of these. All right, now moving on, keeping a good pace here, just trying to get you guys into this and get you guys really thinking. So the next slide that we have here is our intersection of an ellipse. So an ellipse, I'm pretty sure many of you have heard of, but you're really curious, what exactly defines an ellipse? So an ellipse is when a plane intersects only one cone of a double-napped cone, just like a circle and a parabola, and it intersects opposite sides of the cone to generate an elliptical figure. And I'll show you exactly what that means. So just like a circle intersects opposite sides, but it's about the positioning of the plane in relation to the cone itself. So with a circle, the plane is going to intersect a perpendicular, meaning straight, flat across that plane, perpendicular at a 90-degree angle to the central axis or the vertex. However, with the elliptical figure, you have more leniency. A circle is a type of ellipse, as I'm going to say here, also known as an oval, but it has many more properties as well, meaning it can also be classified as this figure as shown here. So it does not necessarily have to be a circle. It can also be other ovular figures like an oval. And it's going to intersect at a diagonal form, intersecting both sides of the generating line and not the base at all. Because if it intersects the base, you're going to have that cutoff and it's going to form a parabola. But it's almost forming a parabola, but it's still a closed figure. So it's going to intersect at a diagonal form without intersecting the base, but two opposite sides of each singular cone, as shown here. And it's not a perfect circle. It's definitely not a perfect circle. It's more of an ovular shape compared to our circle as shown here. However, a circle is still a type of ellipse, but an ellipse is not a type of circle. And that's very important. And how would you calculate the area of a ellipse? So as I show you here, you can calculate it through sectors. So what exactly are sectors? We know that sectors are basically pie pieces. So we're given an ellipse like this. Just going to draw that in a lighter shade. And then we're given these thicker sectors here, basically forming 4 different sectors. We know that these are similar properties to that of a circle, and we would have to calculate it through 4 different sectors. Something that you will definitely cover in higher level math, especially in calculus. So 4 different sectors. All right, on to our next figure, something that you must be familiar with by now, especially in this geometry course, having moved this far through it, or if you come through this journey entirely with me in this course at eCoreAcademy. These are our lines. So my lines are, I'll always stress my thoughts about lines. I absolutely love lines, and they actually develop almost everything in this geometric universe except for conic sections, and that's why they're very important. So lines are technically considered conic sections. However, they're not found in any other types of conic sections. They're building blocks, but they're not found in any other types of conic sections. So let's talk about the intersection of a line. How is a line created in a double napped cone? Because it technically is a conic section. So a line is the intersection of a plane and a double napped cone when the plane only intersects the edges of the combined cones, the generating line. This is basically when the plane overlaps the generating line itself. So this line itself. And what do you think that forms? Of course, it forms another line. That intersection is just a singular line. I just want to highlight upon that. It's going to form that one line as shown here, that one large line. And when it forms that one large line, all you're going to get is one-dimensional line, and that does not have two dimensions or even 3 dimensions. It's a 1D line. And a line is a conic figure not found in any other conic figures. It is a property of polygons and can be expressed through linear equations. So a line is something that has length but no width, therefore it is only 1 dimension, length. And a point has no dimensions, which is our next type of conic section. So that's when that plane kind of intersects this generating line here and forms another line, which gives us the property and generation of a line. And how can lines be expressed? That's going to be expressed through our linear equation. So it can be y equals mx plus b. Other equations like point, slope, and standard form. And this guy right here is going to be our slope-intercept. These are all things you should be familiar from in the basics of algebra. So slope-intercept, we have point slope, and then we have standard. All right, so that's also some very interesting stuff, and that's how the line itself is developed by that unique intersection of the plane with only one section of the generating line. And then finally, we have a point, so the intersection of a point on a double napped cone. So yes, a point is considered a conic section, but it is technically not a figure. It's a placeholder for a location, and it does not have any given measured volume or area. So the point is the intersection of a plane with the vertex of a double napped cone. Keep in mind, remember that vertex is that common point of the intersection between double napped cones, and when we intersect directly on that point, we're going to get directly on that vertex, we're going to get that point. So points make up all existing figures, any figures that you ever come across, any curved figures, or even straight line figures like polygons. They're always going to be existing in every single one because they're just placeholders for a location. We know that figures take up space, and therefore they have to occupy a specifically given location. And those points are basically placeholders for those locations. They do not have a measure of space, but they only indicate location. And if we take a look here, this is our common vertex right here. Vertex. And this is when our plane intersects. Whoa, sorry about that. When our plane intersects through this given vertex. Like that, making it thicker a bit, so trying to highlight upon that. So if we were to have a plane, that plane would directly intersect right here through this central vertex, and of course that place is the contact between both of the double napped cones, and that's also the singular point that we're making concentration upon, like that, just a singular dot taking up space and giving location only, and not taking up space and only representing location as a whole. All right, everyone, so that'll be it for today's video. I hope you guys enjoyed. Please make sure to smash that subscribe button down below, hit that like button on this video, and turn on post notifications by clicking that little bell icon down below, and feel free to utilize that comment section as well. Please check out our website at www.ecoreacademy.org. We have full unlocked access to note sheets, quizzes, and worksheets that go along with each and every single one of our lessons, organized into their own separate core studies taught by us truly at eCoreAcademy. we'll start introducing new faces as well in the teaching realm. Check out our email at eCoreAcademy, or utilize our email at eCoreAcademy.org, at gmail.com, if you have any questions or if you just want to reach out, promoting the website. And also visit all of our socials at Facebook, Twitter, and Instagram. Full link is in the description down below, as well as the website. If you have any interest in seeing what kind of new content we have there, and you can also utilize our platforms to utilize all of those platforms through our accounts to share all of our videos to those who might need it or those who might find it interesting. Once again, everyone, I hope you guys enjoyed. This has been AJay, and I will see you guys in the next video. Peace.